Let's begin with the previous workouts based on the free radical addition reactions. Okay, so this example indicates the difference between the electrophilic addition reaction and free radical addition reactions. So here, when it is a HBr is there, whenever HBr is there, simple HBr is going to give addition product, which is electrophilic addition reaction. So which will be with according to the Markovnikov rule. So Markovnikov product will be going to form. Okay. So if at all HBr in presence of the peroxide, so free radical addition is going to form. So anti-Markovnikov product will be the major product. Okay. So when it is Markovnikov, the addition is going to happen at the more substituted carbon and more stable carbocation is going to form. So benzyl will be the most stable carbocation. So benzyl carbocation will be the intermediate and addition will be according to Markovnikov. If it is this, so most stable radical will be benzyl radical. Okay. So before that, bromine is going to attack. Okay. So this could be the product. Okay. So this is anti-Markovnikov addition and this is oh sorry. So if it is not benzyl, so secondary will be more stable. So that will be the major carbocation and after the rearrangement it's going to become tertiary carbocation. So here carbocation is going to form. So this is going to be the most stable carbocation. So bromine addition will be going to happen here. So final product will be this. Okay. So if it is in free radical fashion, there will not be any rearrangement. So simple less substituted carbon is going to added with the bromine. Okay. So this will be the product. Okay. So next, if it is HBr, simple HBr, it will be electrophilic addition reaction. So most stable carbocation will be tertiary and addition will be at tertiary carbon. Okay. So if it is HCl also, the similar reaction is going to happen. So in that case also, it will be HCl addition is going to happen. So similar to the bromine addition is going to be the final product. Okay. So when it is HBr in presence of peroxide, so it will be going to follow the free radical addition reaction. So less substituted site and without rearrangement it's going to happen. So bromine is going to happen here. Okay. But in terms of HCl and peroxide, there will not be a peculiar peroxide effect with the chlorine system. Only HBr is going to give Kharash effect. Okay. The other reagents will not able to give Kharash effect or peroxide effect. So in that case, the major product will be according to the Markovnikov rule only. Okay. So you need to take care of these examples and these reagent systems. Okay. So let's go with some more molecules. So here, if it is a electrophilic addition reaction, more substituted olefin will be having the more nucleophilicity. So attacking will be at more substituted carbon. So here it will be the final product. Okay. So if it is peroxide also, the more stable free radical is need to be formed. Okay. So in that case, this is the double bond that's going to react in the addition reaction. So the final product will be to the less substituted side only, but attacking will be the same. Okay. So they, whichever they are having more nucleophilicity or more reactivity, that will be going to attack. Okay. So again, electrophilic substitution reaction. So now you need to find out the most stable carbocation. Okay. So which is going to form. Did you try or any guess? So here the most stable will be at this point, okay, carbocation with tertiary, okay, and conjugated system. So addition will be at this point. If it is peroxide, so radical at this point is most stable. So it will be going to give that at less substituted carbon. Okay. So these are the products that are formed from the free radical addition reaction as well as the electrophilic addition reaction. Okay. So here I want to give some more examples. So which are very repetitive in the examinations. So let's try to write some more examples like CH2, CH double bond, CH2, and what. And these are very easy examples also. HCl, HBr, and HBr, ROR under the photolytic conditions. So photolite is going to initiate the reaction, which is a radical initiator, a radical generator. So if at all double bond is here and it is treated with trichlorobromomethane in presence of photolite, what could be the product? So this we've already discussed. So thing is you need to apply once again. So these are the examples. Try to work out. Okay. So next type of reaction are substitutions reaction. So what are substitutions reaction? What are substitutions? So substitution is nothing but replacement. Okay, replacement. So here in a molecule, let's say most prominent example of the substitution is aromatic substitution. So in a molecule, if a atom or if a fragment of a molecule is replaced with the another atom or the fragment, okay, so then it is called replacement reactions or substitution reactions. Okay, so if the substitution is going to happen by one atom onto the position of a molecule or a starting material is called replacement or substitution. Okay, so the reactions of replacement or substitutions are said to be substitution reaction. Okay, if at all if it is a replaceable atom is electrophile and replacing atom is also electrophile, then it is considered to be electrophilic substitution reaction. Okay, electrophilic substitution reaction where an electrophile is going to replace with the another electrophile. Okay, so if a nucleophile is replaced with the another nucleophile, then it is nucleophilic substitution reaction. Okay, if a free radical replaced with the another free radical, then it is free radical substitution reaction. Okay, so why can't we replace a electrophile with a nucleophile? We cannot do that. Okay, so because once a electrophile is eliminated, so the resulting will be anion. Okay, resulting will be anion. Okay, so anion can be attacked by the cation, okay, or positive species, but not with the negative species because it is already electron exchange system which will not be attacked by the another electron exchange system. Okay, they will get repulsion. So electrophile will be more suitable for their reactivity. Similarly, in the terms of nucleophile, okay, if a nucleophile releases, it will be going to form a carbocation which needs to attack it by the another nucleophile so that it will neutralize the electron density. Okay, so this is about the introduction of the substitution reaction. So and the types, three types are there: electrophilic substitution reaction, nucleophilic substitution reaction, and free radical substitution reaction. Okay, so we'll go detail about the electrophilic substitution reactions. Okay, so in electrophilic substitution reactions also more prominent reactions are aromatic electrophilic substitution reactions. Okay, so when it is about the aromatic, we are going to get the idea of benzene systems. Okay, so benzene systems, when it is halogenated or when it is hydrogenated or when it is sulfonated, nitrated, okay, those all are through the aromatic electrophilic substitution reactions. Okay, so basically aromatic electrophilic substitution reactions will have three steps. So here in the first step, electrophile generation. Okay, electrophile generation or formation of the electrophile. Second step is the formation of sigma complex. Okay, sigma complex. We will be going to see what is sigma complex. Okay, next, third one is removal of H place or and the replaceable electrophile. Okay, so let's begin with an example. Like here I am taking benzene. Okay, and treated with electrophile. Okay, so when it is a electrophile, benzene will have the electron density. Okay, that's why it is capable of electrophilic substitution reaction. Okay, so one more thing, whenever a donating group attached to that, okay, donating group is attached to benzene, is going to increase the electron density, which in turn increases the electrophilic substitution reactions. Okay, so it must have the electron density so that it can be attacked it can attack the electrophile and it can be replaced by the another electrophile. Okay, so this is going to act as a nucleophile and will be going to take up the electrophile. Okay, so here it's going to get the positive charge. Okay, so it's going to form in this way. Okay, so when it is forming the carbocation, there would be a delocalization possibility. Okay, there would be delocalization possibility, so that it's going to stabilize. So here it was a double bond and here it was a electron. Okay, this again it can delocalize. So carbocation will generate here. Okay, and the double bond is going to generate here. Electrophile will be here. Okay, so again delocalization resulted into the similar kind of system. Okay, so till it generate similar molecule or similar system, it's going to delocalize. Okay, so that it can get number of stabilized forms or number of forms which are developed by the resonance. Okay, so these all forms are said to be sigma complex. Okay, sigma complex which are formed by the sigma bond of the electrophile. Okay, so after the stabilization through the sigma complex, okay, so it's going to result into the product. So by the elimination of H place. Okay, so H place is going to leave out here, so resulting will be the double bond will stay here. So already present double bonds are there. So finally a hydrogen is got replaced with the electrophile. Okay, so the first step, generation of electrophile, that we will be going to discuss how it is going to generate with the live examples. Okay, and the second step, formation of sigma complex. Here you can say, able to see what is sigma complex and how it is going to form. Okay, so sigma complex is going to form by the formation of sigma bond between the electrophile and the benzene system. Okay, so in third step, removal of H place or removal of already present electrophile. Okay, that is what leavable electrophile. Okay, generally benzene is going to replace the hydrogen. Okay, with the incoming electrophile. Okay, so this is about the aromatic electrophilic substitution reaction. Okay, so it's going to happen with the three steps: electrophile generation and formation of sigma complex and removal of H plus. Okay, so basically when I replace a hydrogen, okay, so if I replace the hydrogen of the benzene with the deuterium, okay, so here when it is carbon deuterium bond and carbon hydrogen bonds are compared. Okay, so generally carbon deuterium bond breakage will be difficult when compared to carbon hydrogen bond. Okay, so when the reaction is just depends on the hydrogen bonding breakage. Okay, I'm sorry, so carbon hydrogen bonding breakage, so then it will be reaction becomes slower by the replacement of the deuterium. Okay, so when a heavy atom is replaced with the smaller atoms, it gets slow end of that reaction. But uh, when the deuterium isotope is replaced with the hydrogen, okay, so deuterium is heavy, so it needs to be replaced, it needs to be slowed. Okay, so reaction should get slow if it is having isotopic effect. Okay, if it is having isotopic effect, it must become slow. So what is isotopic effect here is replacement or change in the reaction speed or reaction kinetics by the replacement of the isotope is said to be isotopic effect, whether it may be decreased or whether it may be increased. If a isotope is replaced at the point where it should change or it should alter the reaction speed or reaction kinetics, then it is said to be isotopic effect. But in electrophilic substitution reaction, isotopic effect will not be observed. Okay. because the breakage of CH bond is not a slowest step or is not a rate determining step. Okay, so it's not a rate determining step. CH bond breakage will not be rate determining step, so it will not give any isotopic effect. Okay, so what is the rate determining step is the formation of sigma complex is the rate determining step, where only electrophile attachment and sigma complex formation is the slowest process, and no CH bonding is the slowest process. Okay, so one more important point, when it is sulfonic acid or sulfonic acid formation or sulfonation reactions onto the benzene. Okay, sulfonation reaction of the benzene is going to show isotopic effect. Okay, except this, no electrophilic substitution reactions are going to give isotopic effect. So in the sulfonation, why it is going to give or why it is going to change the rate of the reaction is because of the it is a thermodynamic process. Okay, only sulfonation is thermodynamic process. Okay, so all other are kinetic process. In the sulfonation we use heat conditions. Okay, temperature and pressure. Okay, so that's why the sulfonation is going to feasible. Okay, happen, so that in the sulfonation reaction only you will be going to have isotopic effect. Okay, so other than the sulfonation, there will not be any isotopic effect in electrophilic substitution reactions. Okay, so hope you understand. So let's go to the substitution aromatic system. For example, if I take a simple benzene system and if I take electron donating group attached to benzene system and electron withdrawing group attached to benzene system. Okay, so this is 1 and this is 2 and this is 3. If at all I treat with electrophile, okay, so which is going to react, with the electrophile faster, or which is very much feasible or very much reactive in electrophilic substitution reaction. So can you guess? So if it is a system which needs to attract the electrophile, it must be with more electron density. Okay, it must be with more electron density. So the electron density of the second is more because of the electron donating group, which will increase the electron density of the benzene system, which can attack the electrophile faster and which can give electrophilic substitution reactions faster. Okay, so the highest reactivity or highest speed of the second will be more than without any withdrawing group. So when it is withdrawing group, it will be going to withdraw the electron density, which will decrease the electrophilic attack onto the benzene system. So it will be least. Okay, so one will be the in the middle. Okay, so the donating groups, which will increase the electron density, will activate the benzene system towards the electrophile. So they are called ring activating groups. Okay, ring activating groups. Okay, so the withdrawing groups, which decreases the electron density towards the electrophile, so they are said to be ring deactivating groups. Okay, ring deactivating groups. Okay, so here we can classify the groups of the benzene substitutions with the different categories. Okay, so here I am going to give all the categories that you can work out. Okay, so strong ring activating groups are OH, NH2, all donating groups. Okay, so NHR and NR2. Okay, So they can increase the electron density through their lone pairs. Okay. So these are strong activating groups. Okay. So moderately activating groups. So moderately will be OR and O C double bond O, sorry, O C double bond OR and NH C double bond O R. This shouldn't be here. This is also here. Strong activated. By the substitution of R group, OH become more donating type, so it will be strong. Okay. So by the attachment of withdrawing group to a donating group, will decrease the electron density, so they become moderately. Okay. So weak ring activating. Okay. Weak activating. So they are alkyl systems and aryl systems. Okay. Hydrogen in this, it will be neutral, neither donating nor withdrawing. Okay. So next, weak deactivating groups. Okay. Weak deactivating groups. So they are halogens, fluorine, chlorine, bromine, iodine. Okay. So if it is fluorine, it will be going to with deactivate more when compared to iodine. Okay, because of the electronegativity. Okay. Next, moderately deactivating. So here strong withdrawing groups like C double bond O, aldehydes and ketones and carboxylic acids and its derivatives. So derivatives are acid halides, amides, esters, anhydrides. Okay. So these all are moderately withdrawing groups. Along with them, cyanide is also a moderately withdrawing group and sulfonate also a moderately withdrawing group. Okay. Next, strong withdrawing groups are strong deactivating groups. So they are NO2 and positive charged systems, NH3 and NR3+. Okay. So the thing is, the right side, sorry, left side groups which are donating, okay, and moderate which are activating, okay. So here we are also including the weak activating or weak deactivating, okay. So these are all going to direct the incoming group, okay. So in electrophile, if a group is there, for example methyl group is there, so it is going to act like a weak activating, okay. So it will activate the ring system, okay, weakly, okay. And whenever a electrophile, another electrophile is going to added up to the system, so it's going to direct the incoming electrophile at ortho position and if possible para position, either of the one, okay. So these all groups are said to be ortho and para directing. Directing means the group which is already present on the benzene system will direct the incoming group's position, will determine the incoming group's position based on the electron density change, okay, based on the electron density, okay, or based on the conjugations, okay. So alkyl is a ortho para donating, so it will direct the incoming electrophile to the ortho and para positions, okay. So left side groups will direct the incoming group to the ortho and para position, whereas right side groups will direct the incoming group to the meta directing, okay. So these all are said to be meta directing groups, these all are said to be ortho and para directing groups, okay. Take a screenshot and make a note of each and every group because they are useful further in many ways. Okay, so classify them according to ortho and para directing tendency and meta directing tendency. Okay, so at least one question will be there in your examination based on the directing tendency or based on the major product based on the direction of the group already present. Okay, so these are very important. Okay, that you must note every functional group and their direction tendency. Okay, so how we will be going to apply? So here are two types of questions you can expect from this groups. Okay, this table. So the first one is reactivity order of given molecules towards electrophilic substitution reaction. Okay, so so how to define the reactivity? So simply the reactivity of the benzene system is depends on the activation or deactivation of the group that is present. Okay, so the group which is with most reactive, most activating. Okay, the group which is with most activating will be highest reactive. Okay, so among these all groups, which is strong activating groups, so this is hydrogen, neither activating or deactivating. OH, strong activating. Methyl, moderately, weak activating. Okay, so NHC double bond OCH3, moderately. Okay, so this is weak deactivating, this is moderately deactivating, this is strong deactivating. So highest reactive will be this one, which is a strongly activating group. Okay, next moderately, next weakly. Okay, next uh, neither activating nor deactivating, next weakly deactivating, next moderately deactivating, and next strongly deactivating. Okay, so this is the criteria. Based on this there would be the question types will also form. Okay, so other type will be directing tendency. Okay, so reactivity and directing tendency. In tomorrow's class we will be going to see the directing tendency and their examples and examples of the electrophilic substitution reaction. Okay, so in today's class you need to work out the substitutions and their directing types. Okay, so here I am also giving reactivity based questions towards the ESR. So select most reactive towards the electrophilic substitution reaction. So NS2 NR3 plus ARB. Next question, which of the following is not orthoparadirectic? Option A, CCl2, and B, C double bond NH2, C, C triple bond N, D, NH3 plus, E, 5. And, not a meta directive. So by tomorrow you must work out on these groups and you must able to decide whether which is a orthopara, whether which is a meta directing group. Okay, mechanistic properties and everything we'll be going to see tomorrow. Okay. So write your responses and try to work out so that we'll be going to discuss more and more. Okay. So with electrophilic substitution reaction, you will gain much more knowledge based on the aromatic chemistry. Okay. So hope you catch every session of this types of reaction. Okay. And if any doubts are there, you can just mail to me. Okay. So or you can send a WhatsApp. Who are having WhatsApp facility difficulty, then they can mail on. Okay.